All right, let's see if this works. All right, let's see if this works. Yeah, okay, it definitely works. Nice. Yes, all right. So yeah, I just found this book on the internet, like going through deep learning and stuff, and I generally want to learn this from a mathematical point of view. So that's basically what we're gonna do. This from a mathematical point of view. So that's basically what we're gonna do. This. Yeah. All right. Yeah. The human visualist is one of the worst. Okay, so this is actually very fundamental. They actually explicitly moduled the neural network based on the neurons in a human brain, so that's very good to know. By handwriting digits, most people effortlessly recognize those digits as This is deceptive. In the hemisphere of our brain, humans have a primary visual cortex, also known as V1, containing... Okay, let's write that down. Containing let's see, 400 million neurons, right? With the tens of billions of connections, right? I spelled that super wrong, but I know at least what it means. Good. But well done, right? And yet, human vision involves not just V1, but the entire series of visual cortexes. Involves all visual cortexes, which is V1 to 2, 3, 4, and 5. Do progressively more complex image processing. We carry in our heads a supercomputer tuned by evolution over hundreds of millions of years and superbly adapted to understand the visual world. Recognizing handwritten digits isn't easy. Rather, we humans are stupidly, outstandingly good at making sense of what our eyes shows us, but nearly all the work is done unconsciously, and so we don't usually appreciate how tough a problem our visual system solves. The difficulty of visual pattern recognition becomes apparent if you attempt to write a computer program to recognize digits like those above. What seems easy when we do it ourselves suddenly becomes extremely difficult. Simple intuitions about how we recognize shapes, like a 9 has a loop at the top and a vertical stroke in the bottom right, It turns out to be not simply to express algorithmically. When you try to make such a rule precise, you quickly get lost in a morass of exceptions and caveats and special cases. It seems hopeless. Right. Neural networks approach the problem in a different way. The idea is to take a large number of handwritten digits, known as training examples. Yeah, and then develop a system which can learn from these training examples. In other words, neural networks use the examples to automatically infer rules for recognition handwritten digits. Furthermore, by increasing the number of training examples, the network can learn about handwriting and so improve its accuracy. So while I have shown just 100 digits above, perhaps we could build a better handwriting recognizer by using thousands or even millions or billions of training examples. In this chapter, we will write a computer program implementing a neural network that learns to recognize handwritten digits. The program is just 74 lines long and uses no special neural network libraries, but this short program can recognize digits with an accuracy of over 96% without human intervention. Furthermore, in later chapters, we will develop ideas which can improve accuracy to over 99%. In fact, the best commercial neural networks are now so good that they are used by banks to process check queries and by post office to recognize addresses. We are focusing on handwriting recognition because it's an excellent prototype problem for learning about neural networks in general. As a prototype, it hits a sweet spot. It's challenging. It's no small feat to recognize handwritten digits, but it's not so difficult as to require an extremely complicated solution or tremendous computational power. Furthermore, it's a great way to develop more advanced techniques such as deep learning. And throughout the book we will return repeatedly to the problem of handwriting recognition. Later in the book we will discuss how these ideas may be applied for other problems in computer vision and also in speech and natural language processing and other domains. Of course, if the point of this chapter was only to write a computer program to recognize handwritten digits, then this chapter would be much shorter, but along the way we will develop many key ideas about neural networks, including two important types of artificial neurons, the perceptron and the sigmoid neuron, and the standard learning algorithm for neural networks, known as stochastic gradient descent. Throughout, I focus on explaining why things are done the way they are, and on building your neural networks intuition. That requires a lengthier discussion of than I just presented. The basic mechanics of what's going on, but it's worth it for the deeper understanding you will attain. Amongst the payoffs by the end of the chapter, you will be in the position to understand what deep learning is and why it matters. So we start with perceptrons, right? So the perceptron were developed in the use of models of artificial in this book. Okay, so a perceptron takes several binary inputs and processes a single binary output. An example, showing the perception has 3 inputs. In the general, it could have even more or fewer inputs. I think we should probably also write the mathematical definition of this. I guess W is for the weight and the X is for the input rate. That makes sense. So I guess it probably, yeah, so the neural's outputs is either 0 or 1, and it is determined by whether the weight sum, which is this mathematical function, is less than or greater than some threshold value. Just like the weights, the threshold is a real number, which is a parameter and of the neuron. To put in more precise algebraic terms, that's all there is to how a perception works. So we know that the X is the input, which can be anything. Anything. And then we have the weight. Which can be is a real number. All right. Or maybe you can think about perception. Okay, so we are gonna make a decision to go to a cheese festival, and we are basing our decision on 3 different factors. I guess that is the input, and then the weight is like how much the input actually matters, I guess. So is the weather good? Question mark. Does your boyfriend or girlfriend want to accompany you? And is the festival near the public transit? You don't own a car. We can represent these factors, 3 factors, by corresponding binary variables. Yeah, that is basically what I said. For instance, we have that x1 is equal to 1 if the weather is good, right? Which is this one here. And then we can, and it is 0 if the weather is bad. Okay, so we have like 2. What is it called? It's a term in discrete math. It's called utsaga. What is utsaga in English? Statement, right? Or declaration. That makes sense. So we have 3 different statements, and depending on if they're true or not, the value will become either 0 or 1. That makes sense. And then we have weights, which makes the increase or decreases the importance of that specific statement, right? I guess. Now suppose you absolutely adore cheese so much that you're happy to go to the festival even if your boyfriend or girlfriend is uninterested, and the festival is hard to get to, but perhaps you really love bad weather and there's no way to go to the festival if the weather is bad. You can use perceptrons to model this kind of decision making. One way to do this is to choose a weight. So W1 is equal to 6 for the weather, and W2 is equal to 2, and W3 is equal to 2, okay, for other conditions, right? The larger the value of the weight indicates that the weather matters a lot to you, much more than whether your boyfriend or girlfriend joins you, or the nearness of the public transit. Finally, suppose you choose a threshold of 5 for the perceptron, with these choices and perceptrons implements the desired decision-making model, outputting 1 whenever the weather is good and 0 whenever the weather is bad, right? It makes no difference to the output whether your boyfriend or girlfriend wants to go or whether the public transit is nearby. By varying the weights and the thresholds, you can get different module decision-making. For example, suppose we instead choose the threshold of 3. Then the perceptron would decide that you should go to the festival whenever the weather was good, or when both the festival was near the public transit and your boyfriend or girlfriend was